Testing, testing, 1, 2, 3, testing, testing! How is everybody today? Hopefully still alive. I realize it's getting pretty close to the exams. I hope everybody, those of you who are capable of it, are working on your exam beards at this point, because, you know, I feel like it's only well and good, even if everything is at home this semester, that everybody starts to let their personal hygiene slide just a little bit around exam time. I think that's part of the whole university experience. Yep. So, no new announcements today. We can get right into the lecture material. I will preface this whole business by saying the stream is still not fixed completely. I've adjusted some settings in OBS that'll hopefully allow the stream to kick back in more quickly, should it be cut out, but it's sort of, it's the ongoing saga of me fighting with my ISP continues. They will have sent, like, they're sending me a new modem. It took them a couple of weeks and 2 technician visits to figure out that it was the modem, which is something that I could have told them from the start. But, you know, so hopefully I'll get my new modem just in time for classes to no longer be necessary. But, yeah. Anyway. How is everybody? Could I have someone please say something in the chat, just to make sure that you guys are in fact alive? I would appreciate it. So, so, today we are probably going to spend a lot of time on inheritance. Inheritance is a very important and proud topic in the history of object-oriented programming, so, yes. You are alive. Good. It is good to be alive. Although you may not think so at the moment, I can guarantee you that it is, you know, it is not a terrible thing to be alive. So, we kind of got cut off the last time, so I'm just going to go over the last few slides. Or, you know, I'll review friendship quickly. So, in C++, you have protection levels for the various members of a class, right? This is, you know, private versus public, the thing that we've been doing. Private members are not accessible outside of the class. They are kept within, they are private. However, in C++, it is possible to designate another class or a function as a quote-unquote friend of a class that contains private members. A friend function or a friend class has access to the private members of its friend. However, it's a unidirectional relationship. It's not a bidirectional relationship. So if class A declares class B as being a friend, that gives B access to A's private members, but A does not receive in turn access to B's private members. B would have to voluntarily declare A to also be its friend. So friendship is by default unrequited in C++. So that's cool. Here is an example. If we have a class A, which has a private member Q, and a public method, which, well, that's the constructor, it declares B, the class B is a friend, then when you declare class B, it also has a private member B and a public method show A, which takes a reference to an object of the class A. It then writes to standard output, A at A is whatever X at Q is. That should say Q right there. So, if you were to, in main execution, declare an object A of class A, an object B of class B, on B, invoke the method show A and give it an object of class A, the object of class B has access to its private member, therefore it is shown. Otherwise, this would trip an error. So, yeah, friendship. Despite being a private member of A, B is given access to A's private member Q. The idea of friendship between classes is a somewhat controversial topic within the broader object-oriented community, as it would seem to violate the principle of encapsulation. Just to recall, the principle of encapsulation is the idea that when you are constructing a class, ideally what you want to do is you want to envelop the information in that class and provide hard boundaries around it so that that data can only be accessed through specific means of interaction. It's kind of like cells in biology. In biology, a cell has a cell membrane, and that keeps the stuff that's in the cell from being in the stuff that's outside the cell, and vice versa, right? It provides a barrier to the contents of the cell. However, in cellular biology, you have various proteins on the surface of a cell which provide channels for various types of ions and molecules, including adenosine triphosphate and other cool stuff in general. And the cell works because under normal circumstances, things get into the cell only via these specified channels. Things can't just insert themselves into cells willy-nilly. There are things designed to insert themselves into cells willy-nilly. However, they have to they have evolved specifically for that purpose to take advantage of the molecular structure. Those are, things like viruses. But anyway, so that's the idea, is you want to control access. And friendship seems to defeat the purpose somewhat because, if you declare a function as a friend, it's sort of outside of the definition of the class, and it's like a backdoor in almost, kind of. And generally speaking, you don't want to have backdoors into software. Yeah. Well, anyway, enough said about that. Boop. Boop. So, in the previous example, we did a thing that perhaps we haven't seen yet, and that is passing by reference. So in C++, you have the ability to pass by reference essentially in two ways. One is to sort of spoof passing by reference in the same way that C spoofs passing by reference. C++ is C++. So you have the mechanism for passing by reference that was available in C, and that is passing around pointers. Oh boy, everybody loves pointers, I'm sure. So when you have two arguments to a function that are declared as pointers, what you're passing into that function are, in fact, the values of pointers. You're still passing by value, but you're passing by value memory addresses. So that's fine. if you want to use a function like that, you have to you have to pass it in the, you have to apply the address of operator to the argument that you want to put in. And then once you're in the function itself, these pointers are going to have to be dereferenced in order to extract the actual data that's at the memory address pointed to by the pointer. So, this is fine. It works, but it's kind of clunky. And generally speaking, it's not a good principle of software design to have to require a particular thing to be done to an argument before it's passed into a function. Hypothetically, if your function requires specific actions be performed on the input before they are received by the function, generally speaking, that's a good candidate for stuff that you would include in the function itself rather than prefacing the function. Like, for example, if if you were doing some calculation that might result in a zero division error, what's the better solution? To check for the zero division error possibility outside of the function before the information is passed into the function, or to check for that functionality inside of the function itself? Obviously, it's inside the function itself, because if it's inside the function, it will never be forgotten by a programmer, and therefore the zero division error will be much, much less likely to occur in the future. So this is kind of a similar idea to that. In C++, we now have an alternative that does not require pointers. It's called pass by reference. So if you want to establish a parameter as being passed by reference, rather than including the star after the type, you include the ampersand character after the type. This tells the compiler this is a pass by reference. And let us recall what the advantages of passing by reference are. When you are passing by reference, let's say Q and R, if Q or R are modified directly within the context of the swap operation, those changes are seen in the global context, because what has been passed into the function is not the value itself, but a reference to the location in memory where those variables are being stored in global memory, or in this case, in the stack frame that corresponds to main. The alternative, pass by value, if you want to, so if this swap operation, first of all, swap operation wouldn't even work if it were pass by value, but let's say that it was. You would pass in this x and this y, and then you would have to do some calculation, and any return value would have to be returned explicitly using a return statement. Whereas, when you have passed arguments in by reference, those arguments are implicit return values of the function. So, in the context of a swapping operation, obviously when we swap, all we want to do is exchange the values stored at two addresses in memory. So, it doesn't even make sense to think about that in terms of a return value, because what would you be returning, right? So yeah, I have a question. So if ampersand is now used to pass by reference, how would you get the address of something? The same way! Again, everything still works just like it does in C. So if you want to access the memory address of a particular variable, you still use the ampersand operator in order to do so. It's kind of like how in C, there's a difference between star as used by the dereferencing operator and star as used by the pointer declaration mechanism, right? So within this context, we're declaring a pointer, but within, like, if within main, for example, we had, star Q, we would assume that Q was a memory address, and then we would attempt to dereference that memory address. We're establishing a sort of, shall we say, a symmetrical case with the ampersand address of operator. So address this within the context of an expression, that still means give me the address of that. However, within the context of an argument declaration, this now means this is being passed by reference. So hopefully that answers your question. So how is this different from using pointers? Well, the things that you can do to pointers cannot be done to something that has been passed by reference, i.e., you can't perform pointer arithmetic over them. You can't assume it's uninitialized to null. All kinds of, like, you can't reassign pointers. You can't, point. They don't point to structures or anything like that. So basically, what C++ is doing is it's taking all of that pointer junk and handling it in the background so that you can use a variable that's passed by reference the same as you would use any other variable. You don't need to dereference them, so references don't need to be dereferenced, ironically enough. References can't be uninitialized or point to something that isn't a valid memory sector. So a pointer can be uninitialized. It can point to something that isn't valid memory. It can be null, etc., etc. A reference, this is never the case. A reference always points to memory that exists because it had to have existed in order to be passed as an argument, right? References lack the flexibility of pointers, including dynamic allocation. So, if your algorithm is something like some of the stack operations that we were doing in C, you wouldn't want that passed by reference because in order to do a push operation on a stack, for instance, what you have to do is you have to good, the stream's still working. For the stack, you have to expand the memory allocated to the stack in order to add another element to the stack, right? You can't do that with a reference because you can't reassign them dynamically using malloc. They're like very transparently just like the variable. It's actually kind of similar to carrying through a global variable, but through a more fixed interface. But yeah. So, using references allows the benefits of in-place memory operations without the muss and fuss of perpetual pointer problematization. So, there we go. Pointers. So, let's talk about inheritance. On to our next topic. Cool. I imagine if anybody has any questions, they will voice them in the chat. I'm going to be very jumpy about checking my feed today. So, inheritance. Inheritance is a very important concept in object-oriented programming. Very important concept. If you take nothing else from the last 2 lectures, learn the difference between inheritance and composition. Oh, there's my mailman. So, in object-oriented programming, we can extend classes using inheritance. In general, inheritance is a poorly understood concept and is often confused with composition. If one class uses or is built from other classes, then you'll want composition. If one class is a variation on another with additional members or with some members redefined, you'll want inheritance. The way that the textbook explains this is it distinguishes composition as a has relationship and inheritance as an is relationship. So if one class has another, that's inheritance. That's composition. So a triangle has 3 points. If a member, if a class is another class, like a more specific version of that class, then that's an inheritance representation. So, a spider is an arachnid. That's an inheritance. Spider inherits arachnid. When one class inherits another, that class gains all of the members of the class it inherits from without needing to redefine them. So, it's kind of like blob monsters. If you imagine the class being inherited as a blob monster, a bigger blob monster, well, actually, it can be a smaller blob monster. Another blob monster comes and envelops the other blob, and that blob is still in there, but externally, all you see is that other blob, right? There we go. Anyway, that's an analogy. Remember, a good old engineer always uses the right tool for the job, and that means knowing when to use inheritance versus composition. There we go. Any questions so far? So, let's talk about spending your children's inheritance. The class which does the inheriting is known as the derived class. The class from which the derived class inherits is known as the base class. These are important terms. The derived class has more specialized or specific behaviors, whereas the base class is more general. This is the mental model you should be using when you're thinking about inheritance. Think about more general versus more specific. The more general it is, the higher up the inheritance hierarchy it will be, and the more things that will inherit from it, and the more base that class is, so to speak. The more specific something is, the further down the inheritance hierarchy it will be, the more derived it will be. So, here's a quick example. Let's imagine we have a class called Animalia. We have a class Arthropoda, which inherits from Animalia. We have a class Chelicerata, which inherits from Arthropoda. We have a class Arachnida, which inherits from Chelicerata. For those of you who know a little bit of biology, these are the phylum genus? I don't know. This is like the classification that eventually will lead you to spiders. Animals, arthropods, chelicerates, and arachnids. Most people don't realize what chelicerates are. But, yeah. It's stuff like horseshoe crabs. Horseshoe crabs are more closely related to spiders than they are to lobsters. But, you know. What is this? Biology class? What the heck is going on? You know what it is? It's like last year I read a book about the Cambrian explosion. I'm looking to see if it's on my bookshelf. And after that, like after reading this book, I have been obsessed with arthropods. I think it's called Wonderful Life or something. But oh my goodness. Where is that darned book? Yeah, there it is. Give me 2 seconds. So, let me see, is the screen. So this is the book. It's called Wonderful Life. It's by Stephen Jay Gould, who is a noted atheist, but that's okay. It's very cool. It's got all kinds of interesting pictures of all of these weird creatures that lived during the Cambrian explosion, which was like one of the initial diversifications of life on the planet, like multicellular organisms on the planet. And during the Cambrian explosion, you see all kinds of interesting developments, like the development of things like arthropods, which is very cool. But anyway, That's not what we're learning about today. I highly recommend the book. If you're interested in bugs, it's a really interesting book. It's called Wonderful Life by Stephen Jay Gould. But okay, let's talk about inheritance. So, you actually have options when you inherit things as well. We may modify the permission level of all members of the base class by specifying either public, protected, or private inheritance. So, you are not permitted to make elements of the base class less restrictive, but you may make elements of the base class more restrictive. Public inheritance is the most common. It's the most common form of inheritance, and like just straight inheritance is public inheritance. But if you specify an inheritance relationship as being protected or private, it will either turn all public things into protected things or turn all of everything private, which is interesting. So, again, you can make less restricted things more restricted, but not the reverse. The reverse direction doesn't work. We haven't really talked about protected members because we haven't really needed to yet, because protected members only are interesting really in the context of inheritance. Protected members are not accessible outside of a class, just like private members, but in contrast to private members, they are accessible to derived classes. So if something inherits from another thing, it gets access to its protected members, but if it doesn't actually get it. So a derived class does not actually get access to the private members of the thing it's inheriting from, but it does get it from the protected members. And you can make the public members more protected if you wish to do so. Any questions? Can I get a thumbs up? Is the stream still going? The stream is still going. Okay. How about here? Have I had any interruptions? I have not had any interruptions. I imagine you guys probably would have complained if there had been interruptions. Okay. Thumbs up? Can I get a thumbs up? Can I get a whoop whoop? So let's talk about an example of how we might break things down according to inheritance. Inheritance within a university. So let's imagine we are trying to construct a system of classes. Oop, is that a thumbs up? Maybe? There we go. Thank you, Anthony. Cool. Excellent. Thank you. Thanks, guys. So, let's consider an inheritance hierarchy of people within a university. So we're making a series of classes that describe people within an organization. So, the most general type of person in this organization is community member. This is a person which has been strictly defined as just a person within the community. The community member can be roughly categorized for the purpose of this example. I know there are more categories than this, but we're trying to keep the example relatively simple. They can be roughly categorized into employees, students, and alumni. Since there are no people who are community members without being in one of these three subdivisions, in this example, we call community member an abstract class. An abstract class, the only purpose of it is to be inherited by other classes. In an abstract class, there's no reason. The programmer predicts that you will never need an actual instantiation of just that class alone. That's an abstract class. Students and alumni require no further categorization, but employees can be either faculty or staff. Faculty can be either administrators or teachers, and it is possible for someone to be both an administrator and a teacher, so we will create a class accordingly. On the next page, you'll see it's called Administrator-Teacher, which is, possibly the least creative possible way of describing that, but personally I find that at a university level, most teaching is administration anyways, but that and making slides. Classes can inherit from more than one base class via multiple inheritance. So this class we're talking about here can inherit from both teacher and administrator. So here's what that would look like in terms of a UML diagram. I know we haven't talked about UML diagrams because, it's not necessarily the subject of this course, but, UML diagrams are the kind of thing where it's like, it's not extremely hard to see what they're getting at. Like, it's a visual, sort of graphical, it's a graphical way of describing the relationships between various elements in software. It's called the Universal Modeling Language, and, I got through my university career just fine, never actually having formally studied UML and yet being presented with diagrams in UML, so don't worry about it too much. So, at the top we've got community member. This is the basis of the base classes. We then have Are we back? Hello, hello? Hello, hello? Hello, hello, hello? Good, okay. Cool, alright. So I was on direct and indirect, yeah. So, alright. We're back. Are we back? Are we back stably? I think we are. Okay. Shut up, me. Okay. Once isn't too bad. If it's only once, that's not too bad. So, the thing I was talking about is this hierarchy, right? So this is the instance of multiple inheritance down here. Whereas composition represents a has a relationship, inheritance represents an is a relationship. A tetrahedron has 4 points, so that is composition. A teacher is faculty, an employee, a community member, simultaneously at various levels of abstraction. Community member is the direct base class of employee, student, and alumnus, but the indirect base class of all other classes in the hierarchy. So in this hierarchy, you've got, basically, if you take any particular class in this hierarchy, for example, administrator, the direct base class of administrator is faculty, and the indirect base classes are employee and community member. Administrator-teacher has 2 direct base classes. The operative idea is abstraction. The higher up the hierarchy that you go, the more abstract the concept becomes. Spider generalizes to arachnid, which generalizes to arthropod, which generalizes to animal, which generalizes to living thing, which generalizes to thing, which generalizes to who even knows. This is actually how our brains work. I'm back. Have I been back? Let me just listen back. Am I doing? Yeah, okay. Okay. So, So this is actually how our brains work, and this is the motivation, at least in part, for the production of a system in computers that can simulate how, how things actually work in reality. The human brain is actually among other things, it is a vast and complicated categorization system. Like, a great deal of what the human brain does on a daily basis is it categorizes things. It puts things into categories. It analyzes it, says, you are this, and then associates that idea with the object. This is called thinking, right? So, like, for example, if you were to take a book, there are a set of attributes, features, properties that are common to all of the things that we would consider books, right? Obviously, there is a little bit, like, there's always an exception to every rule, and the difference between a human brain and a computer brain is that the human brain can deal with a little bit of fuzziness in its categorizations, whereas a computer cannot, because computers really don't do fuzzy. They do a little bit, but it's, only if they're told specifically how to, which, to my mind, doesn't quite encapsulate the idea of fuzziness. But anyway, so, oh, there's a fun one right there. So, all books have a certain set of common features and attributes. There are other types of books, like, there are many different types of books, you can have textbooks, novels, joke books, manga, comic books. All of these different types of books are books, and they all share the common set of features. However, if you were to look at it, you would think book often, right? So, yeah. So that's like how the brain actually works. So you should be thinking abstractions. Abstractions are what we're talking about. So, this is good. So we're going to do an example that involves wizards. I hope, do you guys have any questions at this point? Also, do you like my dad joke? Okay. Guess not. So, let's do an inheritance example that involves wizards. Let us create a spellcasting system eerily reminiscent of one used in a popular tabletop role-playing game that shall remain unnamed. Dajic is good. Good! Glad you like. Gotta get my practice in. So, interestingly enough, this was actually a test question, which the 1MD3 class had on their third midterm on this last Saturday. So I've decided to turn it into lecture slides, to minimize mental effort. As long as I think it's a dad joke and not just a joke. Yes! Well, you see, here's the thing, right? Jokes are a thing that's recognized that has several categories, including... Anyway, dad joke inherits from joke is the joke that I'm making currently. So, in this example, we won't worry too much about implementing in-game mechanics. This is mostly just keeping track of information. Obviously, the spellcasting system I'm talking about right now is the one from Dungeons & Dragons, which is a fun game if you've never played it. If you've played it over the internet on, like, one of these tabletop simulators, often what is done is when a person casts a spell, somewhere in a chat box, the description of that spell will actually pop up, and it is still left to the Dungeon Master or the Game Master to implement the effect of the spell, because the effect of the spell is subject to the interpretation of the Dungeon Master. So it's like it's not even necessarily one-to-one. Like a Dungeon Master can interrupt these types of things for plot reasons. So, or for things that people aren't aware of. Anyway, the point is the spell is just gonna print its own description. So we're going to define 3 classes: Spell, Healing Spell, and Harming Spell. Actually, we're not going to do that second one because it's basically just Healing Spell with one statement reversed. A spell has the following data that we need to keep track of: a name, a level, a description, a school of magic, and a casting time. Casting time seems like it would be an integer, but it's actually a string, and spell level here is the only one that's not a string, it's an integer. In the above, Healing Spell and Harming Spell will also keep track of the number of hit points to award/remove from the target, so we're not going to worry about dice rolls. We're just going to call it a straight number for the purpose of simplicity. So, members-only wizard functions. All our spells will have a public cast function. In all cases, casting the spell will print out the spell's description to standard output. In the case of Healing Spell and Harming Spell, cast will take an object of the class creature, which is the target of the spell. We won't define this class in this example, but we will assume that it has a public member hit points. You can imagine that it exists. These 2 derived classes will also modify the HP value of the target creature according to the nature of the magic's apparent. So, here is a class for spells. Class Spell, protected name, level, description, school, and cast time. We're using standard namespace and including IO stream. We have a public constructor, which takes a string, an integer, and then 3 more strings, which are the name, level, description, school, and casting time, respectively. We initialize these values using the initializer list. We don't technically have to. We could do it within the body of the constructor itself, but you guys, I think, you should get used to using initializer lists, or you should get used to seeing initializer lists, as it's kind of the vogue way of doing things in C++. From what I've seen, at least. We then also have a cast member function. Cast directly puts all of this junk into standard output, which just prints the spell in some manner that's pretty. Int main, we shall have spell A. We are just declaring an instance of the spell class and calling it A, and then we are calling cast on that. So, our output looks like this: Dispel Magic, level 3 Abjuration spell, casting time 1 action, etc., etc., etc. So it just prints things out prettily. If we wish to extend our class, we can define a class called Healing Spell. It inherits, publicly, from spell. So, Healing class inherits spell. Healing Spell is a spell. It has a new public attribute called Heals. It has a constructor. It takes the same arguments as the constructor for spell, except it takes one additional one, int, for whatever you want to initialize the healing factor for the spell as. So we initialize heal, but notice here we are invoking the constructor for spell here. This is an important thing to note because you can't actually do that inside the body of the function. It's disallowed. So this is, yeah, you remember earlier when I said that there are some things that you have to initialize in the initializer list, so you might as well get used to the idea of using an initializer list? This is one of those things. So there you go. In addition, we have the cast function, which has been defined here as well. In this case, it takes a creature by reference as a target, and we have spell is cast target, So this is a line. We'll talk about what this line says. And target.hp plus equals heals. Did I... So that should have the creature at target in there as well. That's a mistake. I'll fix that. Sorry, guys. So, in order to invoke this, we define a healing spell. We shall define a first-level spell called Healing Word. We shall define a creature named Gandalf and assign his HP to 30. Seems a little low for Gandalf, but, you know, he is a bit of a frail old man, maybe. No, that's not true at all. He's not frail. But anyway, we are just printing what his hit points are before, we're casting the spell, and then we're printing what his hit points are afterwards. Executing this function, the HP before is 30, we have the description for the spell, and then we have the hit points afterwards being increased by the number of healing points that were given as the healing factor for that spell. Cool, right? I'm just going to finish off this slide, and then we'll call it a day. I'm going to sneeze, though. Pardon me. We know this is an inheritance situation because healing spells are spells with a little added functionality. By making the field of spell protected, they are accessible to healing spell but not outside of it. Notice that the base class must be initialized within the initializer list. Also notice that we can call the methods contained within the base class by entering into that class's namespace. So that is this guy right here. So notice we're using the scope resolution operator, : to get the class spell, to take the class spell and extract from it the cast function of that class. That's how you do that. Incidentally, harming spell would be exactly the same as healing spell, but with the plus equals replaced with the minus equals. This one right here, that would be a minus equals, and all you do is rename this to harming, and you change all the names. So there you go. I think that'll be our lecture for today. Let me see. Thank you. If there are any questions, please let me know. Otherwise, we shall... Before you go, there is one thing I got wrong last lecture. I thought I was under the mistaken impression that the 7th was going to be the last day of classes, which means that we weren't going to have a class next week. But that is not the case. Actually, the last day of classes is the 9th, which probably anybody who knew anything could have corrected me on. I should really know these things. But anyway, so the 9th is our last day of classes. So I'm thinking we make the 8th, our lecture on the 8th, a review session. What do you guys think? You guys think that's a good idea? I'm getting a thumbs up. Okay. Cool. All right. So that's what we'll do. Next day, tomorrow, the next day, December 4th shall be our last day in which we have sort of lecture material, new lecture material covered. So tomorrow will be the last lecture for this course. And then next week on the 8th, we shall have the review session. So there we go. If you have any topics that you would like reviewed from this course, please have those prepared in advance. And I will do my best. Cool. All right. Aside from that, that seems to be everything. So I'll see you guys tomorrow, eh?